All right. So our problem here says water pours into a conical tank of height 10 meters and a radius of 4 meters at the rate of, well, this rate. So this is how fast it's filling up. It gives us a description of our picture of the cone. So let's draw our picture really quick. It's a cone. So there's a cone. It has a height of, what is it, 10? So I'm just drawing my picture here. If you guys aren't copying the problem, that's cool, but at least draw your picture. Okay, 10 meters. The radius at the top is 4. 4 meters? Yep. And then it gives me a rate. Okay, so I always double check to make sure I used all my numbers up there that they give me. So the rate in this case is 6 meters cube per minute. All right, how would you label that rate? If the water is pouring into it at that rate, the volume is changing at that rate? Yeah, so this is another volume one. So dV over dt, which means we need to have a V. What is our V going to be? Is the V going to be the volume of the cone, or is it going to be the volume of the water? Yeah, because the water is the one that's changing. The volume of the cone actually doesn't change. So we're going to say V is the volume of water. Okay, and then we have to identify another variable. Okay, so what's our other variable here? Because when we read our question here, it says that at what rate is the water level rising?
Height of the water.
The height of the water, there you go. So we need an H, and we need a dH over dt. So your H is height, and this is the change in height. I should say height of water. That's important. Change in height of water. Yeah, water height. That's good too. Height of water. Okay, so now I need a formula. I need an equation that relates the V and the H. The volume of a cone. If you guys take out your formula charts that I give you guys, there's one that says it's an algebra formula chart. Well, at the very bottom of it, it gives you geometry functions as well, or geometry formulas. Right. So our relating equation is the volume of a cone, which is 1/3 pi r squared, and you have to multiply it times the h, the height. Okay. Now, what we have here is we have the volume, that variable. We have the h, but we have this r right here. You can't have that r right there. Because we want just the relationship between the v and the h. So how would we get rid of that radius? Okay, now this part is kind of weird. I'm going to need some water in my cone right here. So there's the water right there. Okay, now I want you guys to think of similar triangles. Guys remember similar triangles? Remember triangles?
Oh my gosh, like algebra?
Yeah. Oh, actually, it's a geometry thing. So there's a triangle right here, and there's a bigger triangle right here.
Oh, those?
Okay? So we can use this idea of similar triangles to create a proportion.
I'm 2 years away.
Yeah.
In 2 years. I love geometry.
I hate geometry.
We can plug in the H,
So
right?
let's set up our proportion.
Patey,
Yeah.
can you plug in it?
Here. Okay, so we're essentially setting up a proportion. We have this purple triangle. This purple triangle is a 4 and a 10, right? And because it's a right triangle, I know it's similar to the black triangle right here. So this black triangle, we don't have labels for it. Yes, I did. Okay, this is radius and this is h. Why? How come we don't have exact numbers for those, Mr. Patey? Because we don't know those. The height of the water is constantly changing. So if I were to set up a proportion for this, you can do it different ways. You can say 4 over 10 and then r over h. Or you can say r over 4 equals h over 10. But it doesn't matter because in either of these, if you solve for r, you're going to get the same thing. So if I solve for r right here, I'd multiply both sides by h, right? So that would be r equals 4 over 10 times r. And 4 over 10 is 2 over 5 times r.
You mean times h?
Right. Yeah, thank you. Times h. Thank you. That equals r. I was like, I went to write equals r. I'm like, oh, that doesn't make sense. Okay, so that is my r. So now I can plug that in for r, and then I don't have any more r anymore. Yay. So I have V equals the volume of the water equals 1/3 times pi. Now look at pi like it's a constant there. Okay, and then for the r we're gonna plug in 3 over 5 h. Not is that a 3? No, that's a 2. Sorry, gotta read my writing. 3 over 2 h. And we have to square that thing, and then we're multiplying that times h. So this would simplify. We would get, I'm going to write it as pi over 3, actually,
Yeah, 1.
2 pi over 15, h to the third.
Wait, Mr. Patey?
Yeah,
Can you find h the same way you found radius then?
What happened?
I didn't square it right there.
The book doesn't use fractions, though, does it?
You're right, the book doesn't use fractions, but I like using fractions. Okay, so we have 1/3 times pi, and this would be 4 over 25 times h squared times h. So when I simplify this, it's going to be 4 pi over 75 h to the third. Okay, now some of you guys are you're asking really good questions. It means you're thinking about it. Why don't we just plug in the height right away, right now? Well, if I do that, I'm not going to be able to find a dh dt. I need to take the derivative of this so I have a rate of the height, the rate at which the height is changing. So now if I derive this, I'm going to get dv over dt. When I derive this one, I'm going to drop this 3 down. If I drop that 3, I'd multiply it times the 4, so it would be 12 pi over 75, and h to the second power, and multiply it by dh over dt. So this is the guy we want. So where are we trying to find this rate at? We're trying to find this rate at where the height equals 5. So you're going to plug in the 5 to the h, and we're going to plug in the rate at which the volume is changing, which is what they give us right here. So now I'm plugging in everything. All right. After you find all the variables, you find the relating equation, and then you make the equation so that it only relates to 2 variables that you're working with. We're not working with the radius right now. So we did this thing right here. We did our proportion using similar triangles. Then we were able to simplify it down to this. Then we took the derivative of it. Now we have this. Now we can solve for dh over dt right now, but actually I'll go ahead and do that. So how do I get the dh over dt alone?
Plug in 6.
You divide it.
And then you divide it.
Yeah. So
We do plug in 6. No, you plug in 6 for dv over dt.
dv over dt times, now this h is technically on top of this guy, right?
Yeah.
So I'm going to say it's 75 over 12 pi h squared. Okay, so this is dh over dt. Okay, now my rate is 6, so I can put a 6 in right here. So the 6 is going to multiply times the 75. What is 6 times 75?
Isn't it just like 3 times? So
Oh wait, we can simplify stuff here before I do that. Oh, and let's plug in our h while we're at it.
5 squared, 25.
It's 5, right? Okay, and then this is supposed to equal my dh over dt. So now if we just simplify, do all the calculating right here, we get our answer to the first part of this question. At what rate is the water level rising at this height? Dang. Okay, and then we'll talk about this question tomorrow.
This is fine.
So this is a 25 right here, so that becomes a 3. This becomes a 1, this becomes a 2. So we have 3 over 2 pi equals dh over dt.
Does it matter where you put the pi?
Yes, it does. Because if I took this pi out, 3 over 2 would be multiplying the 1 over 2.
1 over pi.
1 over pi. Yeah, you're right. This part of the problem, it's more, I guess, logical, as you can see when you think about it. When the radius is smaller, the rate at which the height is changing, the rate at which the water level rises, is going to be really quick. And then as you get closer up here, there's more volume to fill before the water level starts, before it rises. So as time passes, the rate at which the water is rising gets smaller and smaller. Now you could test that just by finding the rate, which is what we got right here. Find the rate that the height is changing at a different height. So you just have to plug in some different values for the height when you're over here. See, we take the derivative, then you plug in the h, and the dv/dt stays the same, but you'll have a different h right here, and then that'll result in a smaller rate as you get closer and closer to the rim of the cone.